Thank you for introduction. Today I'm going to give a talk about Hermitian form, Gross-Keating invariant of Hermitian form. But first of all, I would like to recall the theory of Gross-Keating invariant for quadratic form. So let F be a non-Archimedean local field of characteristic 0, and O the ring of integers in F. Q is the order of the residue field of F, and Hn and Do is a set of half-integral symmetric matrices. It is a symmetric matrix B such that diagonal elements are integral and off-diagonal integrals are half integers. And ND means non-degenerate, which means that determinant B is not 0. And the field F is said to be dyadic if F is a finite extension of Q2. So let sim NF be the set of symmetric matrices of size n, and BU is U transpose BU for symmetric matrix B and matrix U. The equivalence class of B is denoted by brace B, which is the set of BU such that U is unimodular. For B and B prime are half-integral matrices, we say that B is equivalent to B prime if B prime belongs to the set of equivalence class of B. So now I define the Gross-Keating invariant of B. So for let B be a half-integral symmetric matrix, then SB is a set of all non-decreasing sequences A1 and so on AN, such that the order of BII is greater than AI, and order of 2BIJ is greater than or equal to AI plus AJ over 2. And S of equivalence class of B is a union of SB prime, where B primes extends over the isomorphic equivalence class of B. It is easy to see that this set is actually a finite set. So we can define a Gross-Keating invariant as the greatest element of SB with respect to the lexicographic order of the for the non-decreasing sequences. Okay. Okay. So by definition, the Gross-Keating invariant is determined only by the equivalence class of B. And B is said to be optimal if Gross-Keating invariant B belongs to S of B. By definition, non-degenerate half-integral symmetric matrix is equivalent to an optimal form. For half-integral symmetric matrix B, dB is a discriminant of B, which is defined by -4 to the n over 2 times determinant B. And split dB is a discriminant ideal of F square root dB over F. And we define xi B by if 1 if square root of dB belongs to f, and minus 1 if f square root of dB over f is unramified quadratic, and 0 if f square root of dB over f is ramified. We call xi B the Kronecker invariant of B. Now we define another invariant, delta B. If B is a half-integral symmetric matrix, we put dB is order of dB if n is odd, and order of dB minus order of script dB plus 1 minus xi B square if n is even. Then the first theorem says that if A is a Gross-Keating invariant B, then A1 plus A2 plus and so on plus n is equal to delta of B. Actually, this theorem is not is difficult to prove, and we need a reduction theorem, which I explain later. Okay. For non-decreasing sequence A, we set GA is a set of unimodular matrix Gij such that order of Gij is greater than or equal to Aj minus Ai over 2 if Ai is smaller than Aj. So this is an open compact subgroup of GLNO. Then the next theorem says that if B is optimal and Gross-Keating invariant B is equal to A, then U be a unimodular matrix, then BU is optimal if and only if U belongs to GA. Okay. For half-integral symmetric matrix B, and M is an integer between 1 and n, then we denote the upper left m by n submatrix Bij by B to the m. For a sequence AI, A2, and so on, an, we put A to M be the first m element of A. Then the next theorem says that if B is optimal and Gross-Keating invariant B is equal to A, and if AK is smaller than AK plus 1, then BK is also optimal and Gross-Keating invariant of BK is equal to AK. Finally, I need a slightly more invariant, and the Clifford invariant B is the Hasse invariant of the Clifford algebra of B if n is even, and Hasse invariant of the even Clifford algebra if n is odd. The Clifford invariant of B is denoted by eta sub B. So let B and B1 be a half-integral symmetric matrices, and suppose that B is equivalent to B1 and both B and B1 are optimal. And let A be the Gross-Keating invariant B, and we assume that AK is smaller than AK plus 1. Then the theorem says, next theorem says that if K is even, then the Kronecker invariant of BK and B1K are equal. And if N is odd, then the Clifford invariant of BK and BK1 are equal. Okay, now we discuss the Ziegler series. The Ziegler series is defined by the integral where psi is psi is the additive character of f of order 0, and the integral is psi of trace br times the index of r O to n plus O to n of On to the minus s dr. This is a local factor for the this appears as a local factor for the Fourier coefficient of the Ziegler series, Ziegler-Eisenstein series. And this integral is convergent if the real part of S is sufficiently large. Then we define gamma of Bx be the polynomial defined by this. If n is even, it is 1 minus x over 1 minus q to the n over 2 xi bx times product of I equal 1 to the n over 2 of 1 minus q to the 2ix squared, if n is even. And if n is odd, it is 1 minus x times product of I equal 1 to the n minus 1 over 2 of 1 minus q to the 2ix squared. Note that this factor is 1 minus q to the n over 2 times xi bx is always a factor of this, so this is actually a polynomial. Okay, so the theorem of Kitaoka, White, and Shimura says that there exists a polynomial of fbx such that the Ziegler series is a product of gamma b q to the minus f times f of b q to the minus s. So this is a trivial factor for the Ziegler series, and the Fourier coefficient of the Ziegler-Eisenstein series is a product of the special value of some Dirichlet function, which comes from gamma of b q to the minus s, and the product of non-trivial part of which is this factor. So we are interested in this polynomial. And since the Ziegler-Eisenstein series has a functional equation, this factor also has a functional equation, which can be described as follows. So let f tilde bx be a Laurent polynomial defined by this x to the minus order of db over 2 times f of b to the q to the n plus 1 over 2x. Then the functional equation says that f tilde bx inverse is eta b to the n times f tilde bx. So in particular, if n is even, this Laurent polynomial is symmetric. And the Clifford invariant appears only when n is odd. Okay. So now I explain the relation of Ziegler series and Gross-Keating invariant. So the polynomial f of bx is determined by the following data. So one is the Gross-Keating invariant of b, and two is the Kronecker invariance xi of b to the k for ak is smaller than ak plus 1, and k is even. And three, the Clifford invariant eta of bk such that ak is smaller than ak plus 1 and k is odd. This invariant does not determine the equivalence course of B, but this invariant actually determines the Ziegler series FBX. Okay. So now I focus on the Hermitian Gross-Keating invariant for Hermitian form. Now let F be a non-Archimedean local field, and E over F be a quadratic extension. And now script D is a relatively different for E over F, and dB is a relative discriminant of E over F, and x to x bar is a non-trivial automorphism of E over F, and pi b a prime element of F, and psi is an arithmetic character of order 0. Okay. Now for matrix X with entry in E, the Hermitian conjugate is defined by x star ij is x bar ji. This is a usual definition. And let B be a Hermitian form, which says that B is equal to B star. And B is called a semi-integral matrix if the diagonal elements are integral, and off-diagonal elements belongs to inverse of D, inverse of the different. This is actually a dual lattice for the lattice of integral symmetric integral Hermitian matrices. And now BU is given by U star BU. This gives a equivalence class of B by U if U is unimodular and this BU is equivalent to B. Then HNO is the set of all semi-integral Hermitian matrices of size n, and HNNDO is a set of non-degenerate semi-integral Hermitian matrices. Now, for Hermitian matrix, semi-integral Hermitian matrix B, xi B is chi of -1 to the n over 2 times determinant B, where chi is the character corresponding to E over F. And now for Hermitian matrix B, delta of B is given by this formula. Order of determinant B times d to the n over 2 minus 1 if n is even and xi B is minus 1. And otherwise, delta B is equal to order of determinant B times d to the n over 2. And one can easily show that delta B is greater than or equal to 0. Okay, now we consider the Ziegler series for Hermitian matrix B. So now the Ziegler series is given by this integral. Now R extends over Hermitian matrix. And now the trivial part of the Ziegler series actually does not depend on B. So gamma x is given by this formula. So a product of I equals 0 to the n minus 1 over 2 of 1 minus q to the 2ix, and product of I equals 1 to the n over 2 of 1 minus lambda q to the ni minus 1x, where lambda is minus 1 if E over F is unramified, and 0 if E over F is ramified. So there exists a unique polynomial f of bx such that bs is equal to, the Ziegler series is equal to gamma to the q minus s, gamma of q to the minus s times f of b to q to the minus s. Then we can define, as before, we can define Laurent polynomial f tilde bx by this formula, where this is x to the minus of EB, minus EB. And EB is the order of determinant B times d to the n over 2. And the functional equation says that f tilde bx inverse is equal to xi b to the n minus 1 times f tilde bx. Okay. If E over F is unramified, then the theory is quite easy. And if B is equivalent to then in this case, B, any semi-integral matrix, Hermitian matrix B is equivalent to a diagonal form, where order is non-degrading. This is called a Jordan splitting of B. And put AI is order of BI. Then the isomorphism class of B is determined by this sequence. In particular, the Ziegler series of B is determined by this sequence. So, yeah?
In this case, don't you need
Yeah. You can define the signature xi of B. You cannot define Clifford invariant for Hermitian matrix. Yeah, so you don't need you just need the signature. But if E over F is unramified, then the signature xi B is just the parity of the sum of A to A1 plus and so on AN. So if E is unramified, then the signature is determined by this sequence. Okay. Now we assume E over F is ramified. So let pi E be a prime element of E, and the order for element of E is normalized such that normalized so that order of pi is 1/2. So now we define the Gross-Keating invariant for Hermitian matrix. So let B be a semi-integral Hermitian matrix, and we can define S of B in a similar way as in the quadratic form. So SB is a set of non-decreasing sequence A1 and so on AN, such that order of BII is greater than or equal to AI, and order of BIJD is greater than or equal to AI plus AJ over 2. And S of equivalence class of B is a union of SB prime, where B prime extends over the equivalence class of B. And this is again a finite set. And the Gross-Keating invariant of B is the greatest element of S of equivalence class of B. And by definition, the Gross-Keating invariant is determined by the equivalence class of B. Okay. Now B is called an optimal form if Gross-Keating invariant belongs to S of B. Now recall that B is maximal if B of U inverse belongs to a set of semi-integral Hermitian matrix for some U, then U must be unimodular. The first theorem says that for a semi-integral Hermitian matrix B, B is maximal if and only if Gross-Keating invariant B is 0. This is quite easy. Okay, now non-decreasing sequence. For non-decreasing sequence A, put M of A be the set of semi-integral Hermitian matrix B, such that order of BII is greater than or equal to AI, and order of BIJD is greater than or equal to AI plus AJ over 2. So by definition, A belongs to SB if and only if B belongs to MA. Okay, now I would like to explain the reduction theorem. Suppose that A1 is equal to and so on AN1, and then it is smaller than AN1 plus 1, and these are equal, and then smaller than AN1 plus N2 plus 1, and so on. So we can divide we can define a block as a subsequence of this. So we said n star S is the sum of V1 to the S of NV, and S block IS is defined by n star S minus 1 plus 1 and so on, n star s. Okay. For involution sigma in a symmetric group Sn, we set P0 is a fixed point of sigma, and P plus is a set of I such that AI is greater than A sigma I, and P plus plus is a set of I such that AI is greater than A sigma I plus 1, and we can define P minus and P minus minus. And P something S is the intersection of P something and the S block IS. Okay. Okay. Involution sigma. So sigma square is 1. Is identity. Is A admissible if this inequality holds for S equal 1 to the 1 and so on R, and R is the number of the blocks. So for each block, this inequality should hold. Okay, for semi-integral Hermitian matrix B and IJ, B sub IJ is submatrix BII, BIJ, and BJI and BJJ. Okay. Now we can define a reduced form of GK type A sigma, where sigma is a admissible involution. If the following conditions 1, 2, and 3, 1, 2, 3, and 4 hold. So the first condition says that if I is smaller than AJ, I is smaller than J, which is equal J is equal to sigma I, then we have a Gross-Keating invariant of Bij is AIAJ, and signature of Bij is equal to 1. And if I is a fixed point of sigma or P minus minus, then order of Bii should be equal to Ai. And if Ij is element of P0 union P minus minus, and I is smaller than J, and suppose also that either I belongs to P0 or sigma I is greater than J, and then Gross-Keating invariant of Bij is equal to AIAJ, and signature of Bij is equal to -1. And the fourth condition is that if J is not equal to I or sigma I, then the order of BijD should be greater than AI plus AJ over 2. I remark that the Gross-Keating invariant of Hermitian matrix of size 2 is easily determined by discriminant or something. So this condition can be actually verified numerically. Okay. Now the reduction theorem says that suppose that B is optimal and Gross-Keating invariant B is equal to A, then there is a unimodular matrix U and sigma admissible involution sigma such that Bu is a reduced form of GK type A sigma. So the theorem says that any semi-integral Hermitian matrix U B is equivalent to a reduced form. Okay. By this reduction theorem, we can show that the sum of Gross-Keating invariant of this is not AN, this should be AI. Sum of I equal 1 to the n of AI is equal to delta of B. And A is a Gross-Keating invariant of B. Okay. To prove analogy of theorem 5 and 6 for quadratic form to the Hermitian form, we need more definition. So let I1 and so on IR should be the blocks for a sequence A, and put PS plus square is PS plus set minus PS plus plus, and PS to the minus square should be defined similarly. And so each block can be divided as a decision sum of these sets. Okay. Now, A admissible involution sigma is called the standard involution if the following conditions hold. So this condition says that these sets should be arranged in exactly in this order. So pair A sigma is called the standard if sigma is a standard A admissible involution. Okay, now let A sigma be a GK type. It is a pair of A and sigma, and put Ci is equal to Ai if I does not belong to P plus, and Ai minus 1 if I belongs to P plus. If A sigma is standard, then this sequence is also a non-decreasing sequence. So now we consider the set of blocks for non-decreasing sequence Ci. And we define n tilde s similarly, and n tilde star s similarly. So define S of S sub n tilde star s by in this way. This is actually an involution of in this symmetry is a involution of size n tilde star s, and this is also a standard GK type of size n tilde star s. So now suppose that A sigma is a standard GK type, And we define a subgroup by in this way. G prime A sigma is the set of G unimodular matrix G such that order of G I J is greater than or equal to Cj minus Ci over 2 if Ci is smaller than Cj, and order of G I J is greater than or equal to 1/2 if Ci equal to Cj and I belongs to P equal and J does not belong to P equal. P equal is the set of I such that AI equal A sigma I. Okay. Now suppose that B is a reduced form standard GK type A sigma. Then B to the N tilde star S is also a reduced form of GK type. GK type A to the N tilde star S and sigma N tilde star S. And B and B prime are equivalent reduced forms of GK type A sigma and A sigma prime. Then both sigma and sigma prime assume that sigma and sigma prime are standard admissible involutions. Then we can show that these groups are the same, and if B prime is equal to Bu with unimodular matrix U, then U should belongs to G prime A sigma. So reduced form of different GK type can be equivalent, but nevertheless we can show that these groups are the same. So this theorem implies that the sequence C is determined by the equivalence class of B. So now this non-decreasing sequence C is called the modified Gross-Keating invariant of B. It is denoted by MGKB. Okay. Now suppose that B is a reduced form of GK type A sigma, and then Gross-Keating invariant of B is A. Then Gross-Keating invariant of B is equal to A. In particular, B is optimal. Reduced form should be optimal. And suppose that B is a reduced form GK type A sigma, and if N tilde S star S is even, then the signature xi B to the N tilde star S depends only on the equivalence class of B. And if N is odd, we can show a weaker inequality. But we don't need this case. Okay. Now we conjecture that the Laurent polynomial f tilde bx is determined by the following data. So the Gross-Keating invariant of B and the modified Gross-Keating invariant of B, and the signatures xi of B to the N tilde star S such that N tilde star S is even. So we can show that this conjecture is true if Q is odd. And if Q is even, we almost proved the conjecture, but I have not checked the details, so I left it as a conjecture here. Okay. Okay, that's all. Thank you very much.
Do you know any applications of these Gross-Keating invariant for Hermitian forms?
Yeah, first application is for Jigger series. Yeah. And as Professor Cho explained, the Fourier question of the Hermitian Jigger series should be related to the intersection number for the similar variety for the unitary group.
And also this type you say is determined by, right? Is the determination given by explicitly or?
Yeah. We can define an explicit polynomial determined by this data.
I guess it's possible to define the same similar GK invariance for quaternionic Hermitian and quaternionic skew Hermitian.
I don't know. Yeah, it should be easier, I think. Yeah.
There's no more questions. Let's go.